So hello everyone and welcome back to this next video in the DC video series, and we have been simulating a transformer. So this is where we had left off, where we had actually run the transformer simulation, and in this video we will now analyze the response of the transformer. So as before I start the video, a brief background about this project. If you are interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses on the MOOC website Udemy, where you can actually go through the entire course. So the very first course which I have is on simulating power electronic circuits using Python. So in this course you can learn about how to install Python power electronics, a little bit of basics of power electronics, and finally there is a case study on how to simulate a buck converter. Right? If you are interested more on the digital processing side or the control side, I have another course which is called Basics of Digital Signal Processing for Power Engineers, and in this course we talk about basics of Python, some basics of signal processing, and eventually there is an entire chapter on how you can design a low pass and a notch filter using frequency response characteristics using Python packages. And finally, which is what is most relevant for these few lectures, I have another course which is simulation of magnetics for power electronics using Python, and in this course I talk about how you can simulate components like inductors, coupled inductors, and transformers using Python power electronics. There's a little bit of basic theory, and finally there is a case study on how to simulate a flyback converter. Right? So the links for these courses are provided in the description for this video. So if you are interested, check out the description for this video. So now let's get back to the lecture. So where we had left off was that we had completed the control code, and we had run the control code and seen that there was no error. So this is where we had left off. Now in this lecture we are going to analyze the response of the transformer. So the very first thing is we had actually run the simulation, and we had verified that the simulation was running without any errors. There were a few errors but we debugged them. Now before we start analyzing, it is important to note that if your simulation is running, that does not necessarily mean that your answer is going to be correct. And we will look into this video. There might be some errors which might pop up, but let's look at the results first, and it's quite possible that there might be an error. So first thing, let me go over to the simulator and click on the run button again. So it says simulation is running. However, do not trust this message. Always go to the command line and check if there is an error. If you don't see an error, then your control code is indeed working. Right? So let's go back to the simulator and let's check out some results. So I'm just going to delete some of these because these were things which I think got added without any other mistakes. So I created this plot of the two voltmeters. So this is voltmeter of winding 1 and voltmeter of winding 2. Let me go over to the circuit and check out what that is. So this is the true winding transformer. So this is the voltmeter winding 1, right? This is the voltage applied to winding 1, and this is the voltage applied to winding 2. So if you are plotting these two voltmeters, essentially what we are plotting is we are plotting the winding voltages. So that's a good place to start. So let's plot it. And let me go over to the file browser. And let's look at the plot, and you see something very different. Sorry. So there's the blue line, which is the winding 1 voltage, and that is around 300 volt. There is the orange line, which is the winding 2 voltage. Right. So now the question is, the winding 1 voltage is around 300 volts, and that is only expected because we are applying a voltage of 240 volt RMS to the winding 1. But winding 2, which is the secondary winding, is 0. That should not be the case. It should also be around 340 because we have a 1:1 transform. So this result is obviously wrong, right? Now what could be wrong? Let's start debugging this. Let me go over to my simulator, stop it. Now what could possibly be a mistake in these simulations? Now anything can go wrong, right? What could potentially go wrong? The first thing you should do is always, when you run a simulation, go back to your control code and look at the control code once, because there is always a potential possibility that we made some little silly mistake somewhere, right? So the best place to start is always go through your control code once. If that doesn't work, then we start debugging it at the next level. So let's look at what's happening. Import math, there's nothing to do, there's just importing the math library. We are defining the time step of this simulation, which is okay. We have the winding resistances, also okay. We have the rated voltages, V1 rated, V2 rated. Also make sure you got the subscripts correct, so that's also okay. The VA rated, which is the volt ampere rating, which is also okay, 10 kVA. We have I1 rated and I2 rated, and these are calculated with respect to VA rated and the voltage rated, which is also okay. The subscripts are also okay. We have the rated frequency, nothing there. Then we are calculating the inductances, the self-inductance of the two windings, right? That is with respect to the voltage rating and the current rating. Again, we got the subscripts correct, so that should be okay. We are calculating the inductances with respect to the reactances, and that also is okay. The subscripts are okay. It's important to note that the subscript should match. It is quite common, especially when you copy paste code, that you might have forgotten to change some of the subscripts, right? So just make sure that has it. Then we go over to calculating the leakage inductance. So again, we are expressing it with respect to the rated voltage and the rated current. Again, we got the subscripts correct, so nothing to do. Then we are calculating the leakage inductances from the leakage reactances. So again, subscripts match, no problem. Then we are calculating the magnetizing inductances, right, with respect to the self-inductance and the leakage inductance. Again, all the subscripts match, no problem. Then we are calculating the resistance, external resistance of the model with respect to the rated voltage and the rated current. Now this is the external voltage of the current source that represents this winding, right? No problem there. Then let's come over and look at our actual control code. So first we are calculating the induced EMF from the winding voltage and the current, right? So basically it is the winding voltage minus a resistive drop, right? That's okay, nothing wrong here. From the induced EMFs, we are calculating the flux linkages. So basically all we are doing is we are integrating the induced EMFs with respect to time, right? The subscripts are okay, nothing wrong. Now, we are now assigning the flux linkages to this current equation. Now the question is, why am I doing this? I am already calculating the flux linkages, and then I am coming here and I am calculating it again. Now you need to know that the currents are zero initially, which means this recalculation sets this flux linkage to zero. This equation has no business being here. The only reason why I wrote this equation was to be able to derive these two equations, right? This equation is a simultaneous equation in these two currents. These two currents are the unknowns, I1 and I2. And the objective behind writing this equation was to be able to write equations for the two currents. So which means that these equations are references for this. They should not be there. So actually I should comment them out. Alright, I should comment them out. So let me comment them out. And then when I come here, I am calculating the two currents, which is basically just psi I2. I'm just taking psi I2 divided by the current, which is psi I1 minus LM2 minus I2. Yeah, this equation seems okay. And finally this substitution as well. And eventually the winding voltage is equal to the source winding is equal to this winding voltage minus the drop across the external resistance. So this looks okay. This was the only major error, right? So now let's run this simulation and check if this error makes it go away. So let's go back and click on the run button again. Actually, now that I think about it, let me delete this and add another one, because I don't think this was something that happened before. Let me go back and add a plot. Let me call this winding voltages. Okay, we have winding voltages. And I just have to add voltmeter winding 1 transformer 1, call it P1, save the waveform, add voltmeter winding 2, call this P2, save the waveform. So now I have two waveforms and I have this waveform called, this plot called winding voltage, which is a little better than calling it just plot. So let me click on the run button. Simulation is running. As always, let's go to the command line, verify that there is no error, and there is no error. So the simulation is indeed running. So let's go and click on the plot button. And here Let's look at what's happening. So now the result, we now have a result, right? See, there is a blue line, there is the orange line. But see what's happening here. The orange line is steadily increasing, and eventually what this is an unstable simulation. See, when you see this envelope continuously increasing, this is a sign of an unstable simulation. So let's go and zoom in between 0 and 0.001 maybe. So let me go and zoom in. We put a very small value and plot it again. Okay, I think what has happened is that it has actually already become unstable. So I'm just going to go click on minus 340, rather minus 350. And let me check it out again. I think I put the range wrong. Let me go do it again. It should be minus 350 to 350. I probably did it minus 350 to minus 350. And here you see. So this of course is not very easy to find out. Maybe I need to plot a little more. And quite often this is how it is. You just have to sort of keep plotting until you can determine some kind of result. Maybe I'll plot up to. So you can even plot up to 1. So let's plot 1 half cycle. And once more 350 minus 350 to 350. So we're trying to plot from the negative peak to the positive peak. And here, now you can see the result is fairly interesting. So this shows clearly, you see the blue line is the applied voltage to winding 1, and that is steady because we are applying actually a 240 volt AC voltage, right? That's why it's steady, because there is a solid AC voltage behind it. Now the orange line, however, you can see it's actually continuously blowing up. It starts with this envelope, but it's continuously increasing in magnitude. This is a case of a system which is almost marginally stable and tends towards instability, right? If it was completely unstable, it would just have blown up immediately. But this is a case of system that is marginally unstable, which means it's on the edge and it just rolls over, right? Now, what exactly is the reason for this instability? Now, instability can be a little difficult to simulate, to actually debug, right? That's why I wanted to show you this exact result. This is how you determine instability. Now, there are several reasons for instability. One way to solve it is to decrease this time step. Alright, that's one way to increase it, because when you decrease the time step and you decrease the integration time step of the simulation, your integration now becomes more accurate. And the result would be that you would now be able to make the system stable, because any inaccuracies in the integration would result in instability. Another thing that you could look into is you can look into this winding. Let's look at what we are actually doing. So if we go over to our circuit, the way we have actually simulated it is we have two voltages. So we have an applied voltage, that is the input voltage, and this winding is a voltage source in series with a resistance, right? So what we have is, we have two voltage sources connected together through a resistance. Now, this resistance therefore determines how weak or how strong this connection is, right? If you have a very small resistor, then the current flowing between two voltage sources can drastically change if there are even small changes in one of the voltages, right? Just imagine two voltage sources connected together through a resistance. The smaller is this resistance, the more sensitive is this circuit. The larger is this resistance, the less sensitive is the circuit. But then again, you don't want something very large either. If this resistance is very large, it may completely kill any dynamics in this circuit. So therefore, we need to choose this maybe a little well. Let's go back and look at our code. So what we would do is, let's go and print it out. Let's go and print these two. So let me just go print resistance winding 1 and resistance winding 2. And let me go back to the simulator and let's click it again. Let's go back to the command line, and this time we now see the results. So you see the two resistance that we have chosen, that is this resistance is mere 5.76 ohms, right? So we have two voltages with a peak of 350 volts with separated by a mere 5 ohm resistance, right? Now, such a system is fairly sensitive, and that could be one reason why we have instability. So what I would do, I would go up and I would increase this by a factor of, let's say, 10. Okay. So now instead of 5.76 ohms, we now have 57.6 ohms. So with this, let's go back and run the simulation. And you see now we have 57.6, right? But most importantly, we need to see if the simulation is stable. So let's go plot it again. And we now have a stable simulation. You see here now, you see these oscillations in the voltage are still present, right? But you see now, instead of the oscillations blowing up, the oscillations are actually decaying, right? They are finally decaying. If you look at the peak here and compare it with the peak here, you see it has decreased. Let's go and plot it again. And now you see the simulation is completely stable. So you see the oscillation exists for one cycle and maybe one more peak. So it's like 1.5 peaks. And after that, the simulation is absolutely stable. So with this, we can conclude that the reason for stability was that the system was very sensitive. And this is one of the things that you need to understand about any simulation, is that there are two ways to simulate a system that is sensitive. If you determine that your system is sensitive and you must simulate a sensitive system, then in that case, you have to decrease the integration time step. However, if there is a possibility of making your system less sensitive by changing some resistances, then we should examine that as well, right? So we now have a stable simulation, which means that we are now a working transformer model. So I will end this lecture here because, as I said, I do not want these lectures to get too long. It's probably already several minutes. So with this, if you have any doubts about what I did or about the code, now this concept of instability and making a system, changing the sensitivity of a system is a little complex, and it may take some amount of experience before you can actually simulate, or rather overcome these kind of instability problems in simulations. So I would only say, if you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you in the next week, where we will analyze this in detail and probably even change the turns ratio and analyze that as well. So thank you so much for watching and see you soon. Goodbye for now.